Hello everyone, welcome to ZK Cryptography, part of the Worldcoin Educate Series. Today we have the special DCbuilder, same as the first workshop. I'm going to invite him onto the stage now.
Hello everyone. So welcome again everyone. So today I'll be talking about zero-knowledge cryptography as part of the Worldcoin Educate series. As you've heard, like the previous weeks, you've been seeing a bunch of different things, right? So I started with the introduction to Worldcoin, then Dan talked about the orb hardware and software, Tongi talked about biometrics, and also one which is fairly relevant to the one that I'm going to be discussing here is the ZKML and MPC discussion that was led together by Daniel and Ryan from Modulus and Lucas from the Tasio team. We'll be talking about ZK, right? So in the first word you say ZKML, right? So there's ZK there also. So I'll be expanding a bit of that topic and what are we doing within that topic within Worldcoin and expand on what we're doing right now. So to start, I think that it's good to just start with a generic explanation of what ZK is all about. It's a fairly loaded concept, fairly loaded topic, very popular, especially if you consider things like zero-knowledge rollups or privacy applications, right? So if you've seen things like you have different ZK VM rollups or scalability solutions, right? Maybe you've heard of ZK Sync or StarkNet or Scroll, Linea. There's a few other different companies building ZK products in the blockchain space. And there is constantly more popping up, and it's one of the hottest topics in the entire space. So I think it's good to just have a general understanding of where this comes from and why is it useful and why people are so obsessed with it nowadays and why people are building with it and why we at Worldcoin are also using this technology to build part of our technology stack, right? So to start, I will explain what ZK is conceptually. The easiest way that I've seen this being explained is with the notion of a probabilistically checkable proof, or PCP. So in the sort of literature, like the cryptography literature of where zero-knowledge proofs first come about, is this notion of a probabilistically checkable proof. So essentially, there's this like easy example that I often use to explain what ZK is, right? So if you see this diagram over the bottom left of what a PCP is, essentially you have two parties. One is called the prover, the capital P over the left, and the other party is called the verifier. And essentially, the general paradigm here is that the prover knows some information that wants to convince the verifier of knowing, right? So I want to prove to the verifier as a prover that I know something. It can be a piece of data, it can be some computation, and there's this interactive protocol where I, as the prover, communicate with the verifier over a few rounds to convince them of the statement. And if they're convinced of the statement, they'll say true, otherwise they'll reject it and say false. One specific example or one actual example of what a PCP might look like is the example of proving to a blind person that colors exist. There's this like really nice example where if you imagine that there is a colorblind person, so they're not able to tell colors apart, and a non-colorblind person, the colorblind person might not believe the person who sees colors that colors actually truly exist. So how would we prove to the blind person, to the colorblind person, that the colors exist? So the way you can start, or you can actually do this sort of protocol, is that you create 3 pieces of paper, and each of them have a different color, right? So the normal, or the person who sees colors is able to tell them apart, right? Like I have a red one, a green one, and a blue one, and I'm able to tell them apart. To the colorblind person, they all look the same, but they can label it 1, 2, 3, and as long as the colorblind person doesn't reveal which papers they've labeled 1, 2, 3 in their own head, now they're able to shuffle them around, right? So I, as the verifier or as the colorblind person, I'm able to shuffle the papers around, and then every time I shuffle them, I show one piece of paper to the prover, and the prover will be able to tell me like, hey, I think this one is red, I think this one is blue, this one is green. And so the likelihood that they guess correctly after the first round is 1 in 3, assuming that we have only 3 pieces of paper, right? So the chance that they guess correctly is 33%. Okay, so I take back my pieces of paper, I shuffle them again, I show another one, and now the prover guesses like green, or says green. If they're correct, the likelihood that they have guessed correctly twice in a row is 1/3 times 2, right? Or 1/3 times 1/3, which is 1/9, right? So the probability each round keeps diminishing, meaning that for every single round that I do, the likelihood that they're guessing correctly is really low. And so you can imagine that intuitively, the more rounds we do, the lower the likelihood is that they're guessing correctly. So let's say if we do 1,000 rounds, it's nearly impossible statistically or probabilistically that they're guessing correctly 1,000 times in a row, because they always have like 1 in 3 chance of guessing correctly. So this is like the notion of knowing something, or knowing an argument in this case, which we're getting to in the next concept. So essentially they know some information, the prover knows some information that the verifier doesn't, and the verifier can be convinced after some amount of rounds that the prover actually knows that colors exist, so they can be convinced. So this is the notion of a probabilistically checkable proof, and it's like how this field generally emerged in literature. There is some cool tricks that allowed you to create the next construction, which is called the SNARK, which is the sort of meat of what we're going to be talking about today. So SNARKs stands for Succinct Non-Interactive Arguments of Knowledge. So knowledge is this sort of thing that I discussed earlier, right? Like the prover knows something that the verifier doesn't, and they're making some argument about the knowledge, right? So they're making a statement about the knowledge they have, and the verifier can be convinced. So we saw that the first protocol, when I'm showing these pieces of paper, is very much interactive. There is a few rounds where the prover and the verifier are interacting, and they're essentially communicating with one another, right? They're interactive protocols. In the SNARK, or Succinct Non-Interactive Argument of Knowledge frame of thought, it's a by definition non-interactive protocol. So the prover is able to create a computational proof called pi, or you can just label it pi, and the verifier will just verify that proof pi, and they will be convinced. The way that this is actually constructed is beyond the scope of this presentation, but for those who might be interested, you can Google the concept Fiat-Shamir transform, which I can briefly just message in the chat if you're curious, or you can ask an LLM or your favorite AI to explain what it is. There is Fiat-Shamir, sorry, give me 1 second. There we go. Fiat-Shamir transform. So there's this cool protocol in cryptography that essentially allows you to turn any interactive protocol to a non-interactive one using randomness. So that's a pretty neat thing. Let me go back. Cool. So essentially, we're able to turn protocols that are probabilistically checkable or interactive protocols into non-interactive protocols using this cool thing. Also, let me probably pull up the questions to another slide so I can see them while I'm explaining, just in case I lose some of you. Cool. Great. Okay. Awesome. That way I can also see when I'm streaming. Great. Sorry about that. And so essentially with this SNARK, a prover can prove to a verifier with just one piece of data, like a proof can vary in size, but the concept is that with just one interaction, the prover can prove to a verifier that they know some knowledge, or they know some data, they know some computation happened correctly. So that gets me to the next concept. So the first word in SNARK stands for succinct. That is essentially talking about sort of the computational intensity, or like how complex it is to create and verify such a proof, right? So succinct means short or small or easy to verify in this case. What succinctness is defined as is that in order to verify a computation, it's a lot cheaper to just verify the computation than performing it myself, or to, for example, verify some knowledge without having me to prove it myself. So you can think of any sorts of kinds of things that we can make proofs about. I can, for example, prove that I know a private key to a public key without revealing it. And this is a thing that calculating it requires you to do a signature, right? So it might be complex, it might be like complicated to do these sorts of things. And so a succinct proof just means that it's something that it's a lot simpler or a lot easier to verify than to compute in and of its own. So this is the notion of succinctness. So the general properties that we care about, I have them listed on the bottom right. So enumerating them, there are soundness, completeness, succinctness, and zero knowledge. So I mentioned succinctness, which just means that there's a small proof in size, like it's a lot less bits to represent the proof than the computation. And there is a fast verification time for that proof. And in computational science notation, there's this like big O of something notation where it talks about the computational complexity of the program. So it's usually polylog of n or constant size, constant time also, O of 1. So soundness, what it means is that a prover cannot craft an invalid proof that the verifier would accept with a very small probability, right? So essentially, it's unlikely or extremely unlikely, like probabilistically unlikely is like 1 in a very large number, meaning that it's like extremely unlikely for the prover to be able to craft a proof that is not valid. So the only way that they can, so that the verifier would accept the proof if the verifier will only accept the proof if it's a correct proof. Completeness, that essentially means that in order for the prover to create a valid proof, they need to know all the information that they're making a proof about. Here I introduce the concept of witness, omega, and constraints, C. That is more of a technicality, but essentially what I'm doing is I have some data that I want to prove some structure of, right? So I want to prove, for example, that I have a private number or like a hidden number that if I add some number to that number, it's equal to 10. And these are constraints, meaning that I'm constraining what the data that I'm making proofs about looks like. And then I can prove to the verifier that my data or my witness or my computation satisfies these sorts of constraints. To go into depth into what these things actually mean, it takes a lot more time, but I'm happy to share some resources towards the end or answer some questions about this. So yeah, that is the second property. So it's, essentially the prover needs to know the thing that they're making the proof about. They're not able to just invent it. And then the last property, zero knowledge, is essentially the thing that we're talking about today, or like what almost the topic is named after. ZK stands for zero knowledge. And zero knowledge essentially means that the prover can hide parts of the information they're making proofs about, but their information always needs to satisfy some constraints or some sort of rules that we've put in place so that the verifier is convinced, right? I can prove to the verifier that I know some number that added with another number, they're equal to 10, but I don't have to reveal which numbers I'm adding. I can just prove to the verifier that I know such numbers. And the good property of this is that I can hide this data or hide this computation without losing this sort of computational correctness or this proof notion. Yeah, I can share the slides. We can do that for sure. Yeah, no problem with that. Or actually, maybe, yeah, I'll share it towards the end. So yeah, so this is like the notion of a SNARK. So SNARKs is the difference between a SNARK and a zero knowledge SNARK is fairly small. A SNARK is a proof where none of the witness or none of the data or none of the computation is being hidden. There's nothing being hidden. Everything is public to the verifier, and the verifier just verifies the proof, and that's it. A zero knowledge SNARK is a SNARK where some of the data is being hidden from the verifier, but the verifier still knows some structure or some constraints that are satisfied by the data that I'm making a proof about. And then there is a slightly different sort of construction called a STARK. The actual reasoning for why it's called different is mostly about the mathematics of how it's constructed, but you can think of it as like the same thing pretty much. Like it's something that allows you to create a proof of computation that has the same properties that we have on the right, but it just uses a different set of constructions cryptographically. For those who are math savvy, SNARKs use elliptic curve cryptography, and they're based off of usually elliptic curve pairings and these sorts of mathematical operations. That's how they get their security properties. But for STARKs, they use hash functions and other constructions. So yeah, so those are like some initial concepts we're going to work with for the rest of the discussion. So on the very first talk that I gave, introducing Worldcoin, I had a slide that looked like this. I don't know if I can zoom while, probably not. So let me just quickly zoom. Let me see, because I can see what I'm streaming. So you can see this diagram. Cool. Right. So on the first slides that I presented and on the introduction, I showed this diagram, right? So this diagram essentially explains like what our architecture looks like and what it does, more or less. And so I want to explain where we're using zero-knowledge cryptography or why. So when you're a user and you download the World app, which is over here, I'm able to now interface with the Worldcoin ecosystem. So what does that mean? With the World app, I can go to an orb and get my World ID verified. So when my World ID is verified by the orb, it will be inserted into, like my public key will be inserted into the set of verified users. And that is something that I will explain a little bit later. I have the next slide, which will explain how that works. But essentially, once I have a set of verified users, I'm able to verify that I am a member of the verified users without revealing which member I am using zero-knowledge cryptography. The zero-knowledge property is the thing that allows me to hide the thing that I'm proving. In this case, I'm able to prove, I'm creating a zero-knowledge proof on my phone as a user that I'm a verified user without revealing who I am. So this is like why ZK is generally useful, right? Like I'm able to hide information without losing trust, right? It's cryptographic trust because I can just verify a piece of math. And if that math holds, then I know that I'm not lying, or like somebody else knows that I'm not lying to them. So I'm proving that I'm a World ID verified person without revealing which World ID verified public key I am. This is like where generally ZK is useful. And so if we move on to the next diagram, let me unzoom. Probably let me make it fit and probably present again. So I see some questions over here. Agnivo, like isogenies, I don't know what you mean by that. If you give more context, I'm able to answer that one. And the next one's Brian, what is the primary goal of Worldcoin? So if you watch the first presentation I gave, that one will give you a much more in-depth explanation. I think like it's besides the point because like it takes a while to explain. So if you can just rewatch the first one, I think that would be useful. How does Worldcoin ensure a unique digital identity for each user? So the orb, this hardware device, I have it with me. I can maybe show it a bit later, but it's essentially this hardware device that is able to verify two things, that there's a real person in front of it. And the second thing is that using biometrics, which we also had a presentation on from Tanguy, you're able to verify that the person is a unique person. And so with those two things, you're able to deduplicate the set of public keys that are verified on-chain. So what role does zero-knowledge proofs play in the Worldcoin ecosystem? Okay, so that's what this talk is about. I'll get into that a bit later. How does Worldcoin address privacy concerns associated with biometric data? This is a good question. We have a lot of blog posts about that. In the white paper itself, it goes into quite a bit more in depth. But essentially, it's a combination of multi-party computation and zero-knowledge cryptography. So the iris codes, which is the thing that we talked about in the biometrics presentation, are stored in a so-called multi-party computation fashion. So they're stored in an encrypted fashion. There's no plain text of the iris codes. And then using zero-knowledge cryptography, you're able to prove inclusion in a set of verified users without revealing who you are. So those are like the two main privacy components. There's, of course, a few others, like on the orb itself, there's privacy embedded into it and a few other places, but the white paper has more details on that. And I recommend you watch the previous talks, which talk about MPC and how that works, and also how the biometrics work as well. So you have a notion of what that is. Agnivo, in SNARKs, you said elliptic curves are used, and in STARK hash functions. About the former, what about elliptic curves are used? Is it isogenies? Yes. So for that, I'm not sure if I'm able to explain that in a short amount of time. We can follow up after this. It will just take too much time to explain these sorts of things. But yeah, I'm happy to get into that later. Maybe you can DM me on my Telegram after this. Cool. So moving on. So what I wanted to explain when it comes to verifying that you're a unique person without revealing who you are, we use this protocol called Semaphore. So Semaphore is a protocol that was built by the Ethereum Foundation, and there's a specific team within the Ethereum Foundation called Privacy Scaling and Explorations Group. So this group has a specific team which is called Semaphore. That's like it's a circular definition, but essentially this team built this protocol. And what this protocol allows you to do is it allows you to prove that I am a member of a set without revealing which member I am, right? So if I have a group of 10 people, I can prove that I belong to that group without revealing which member I am. So you, as someone like who is not in the group, I can prove to you that I'm a member of this group without revealing which one it is, and I have which one I am, and I can do that without revealing anything about myself. So that is like the property of Semaphore that allows you to do that. So how does Semaphore actually work? There is this data structure called the Merkle tree. I pulled the diagram from Wikipedia over on the right. Essentially, the way that a Merkle tree is constructed is that you have some set of elements. These are like these L items in the bottom, L1, L2, L3, L4. And if you hash each element and then hash the sibling of each element together, you're able to create this tree-like structure all the way to a top hash. And with that, essentially what you're able to do, the good property of a Merkle tree is that you're able to verify inclusion in constant time, right? So if I get the hash of my specific, let's say that all of these nodes at the very end are public keys, right? So it can be my public key, it can be Brian's public key, Agnivo's private key, Emma's private key. So all of our private keys are in this Merkle tree, and we're able to hash them to create the Merkle tree. And the good thing is that, let's say that I want to prove that my public key is in the Merkle tree. What I do is I hash my public key, and then I hash everybody else's, like the sibling of each of my structures. So like the sibling would be like, if this is mine, then the sibling is the one. Sorry, I think the mouse is not shown while I do in full screen. Okay, let me do this. Now you can see my mouse. So if I have this one, so this one is my public key. If I hash my public key, the sibling would be the one next to me. So if I hash this one and I hash this one, I get this parent hash. And then if I also get the hash of the sibling to my parent hash, I'm able to reconstruct the top hash. And so this is, if I get all of the sibling hashes, I'm able to reconstruct the top hash. And if I'm able to successfully reconstruct the top hash using my own public key, that means that I can prove to anybody else that I'm part of the tree. However, in this Merkle proof, as it's called, I'm revealing which leaf I am. I need to share which public key I am in the tree in order to prove to somebody else that this is how it works, that I am in the tree. So the innovation of Semaphore is that you're able to prove that you own a specific node or a specific public key in the tree without revealing which one it is. But you can prove to someone decisively using zero-knowledge cryptography that you actually have that. So this is like the main property of Semaphore that we're using within World ID, our proof of personhood protocol, to allow you to prove that you're a unique person without revealing who you are. So this is the step number one. So now you can prove inclusion. This is like the main property of ZK that we're using here. Privacy preserving proof of inclusion in a set of verified humans. And then the second part is that there is this construction called the Nullifier Hash. And what a nullifier is, I describe it here, over here. So a nullifier is a hash of a private key, an action ID, and an app ID. So maybe you've heard of Ian's presentation. Maybe you listened to Ian's presentation about World ID use cases. I think it was yesterday, if I'm not mistaken. So in the use cases one, you're able to see what World ID can be generally used for, right? So that essentially means anything where you want SIB resistance or one person, one action type protocols. So you can think of voting mechanisms, right? So one person, one vote, like democratic voting. So the way that you're able to prove that only a person has voted only once is using this sort of nullifier structure. And this is just done with the hash of the user's private key, an action ID and an app ID. So the action ID and app ID are tied to whatever the integration is. So it can be like this governance vote, like this democratic vote. and the hash of the private key is like just the hash of the user. So the property of the nullifier is that it's deterministic. So for every single action and for every single user, I'm only able to generate one type of hash. Essentially, if the protocol keeps track of these hashes, and note hashes are completely random pieces of information, like they don't reveal anything about you, it's completely privacy preserving. With these deterministic hashes, I'm able to keep track of who has voted and who has not voted without knowing who that person is. I'm able to just say, okay, this has been a unique human because they have a world ID proof, like a Semaphore proof, and I have a nullifier. So together with this inclusion proof in the tree and with this nullifier, I know that there is a unique human being that has not voted before, that is now voting for something. And once they vote, we just log the hash of the vote of the nullifier, and they're not able to vote again, because when you're checking for a vote again, their nullifier will collide against one that I've already seen before, so I know it's the same person voting. I don't know which person it is, but I know it's the same person. So this is like the main use case of Semaphore and main use case of ZK in World ID as it is right now. There's another use case for ZK as well. And note, there's one footnote or one side note is that in the blockchain industry, people use the term ZK for an incorrect thing. So if we go back to the previous slide, there are zero knowledge properties that I'm concealing some data or some witness data from the verifier. So I'm hiding something, but you don't have to. A lot of the ZK use cases in the space, for example, like rollups, they're proving some computation, in this case, like an EVM transaction or a block of transactions on the EVM, but they're not hiding anything. So they're not zero knowledge, right? They're not hiding anything. So we cannot use the term zero knowledge for that because everything is public to the verifier. So in the industry, you might hear people saying that there's a ZK rollup. What they really mean is that it's a SNARK rollup, or it's a validity rollup that is proving that the computation happened correctly, but they're not hiding anything. This is just like a footnote. If you're confused sometimes that people are like saying, oh, this is a ZK thing, but in reality, it's not a ZK thing. It's just because the word ZK is like quite like rolls off the tongue, and it's like good branding, good marketing, so people use it and overload the term beyond the mathematical definition of what it actually means. So in this case, we're actually using ZK because we're hiding the private key. We're proving that it's in the tree of. But in the second use case for ZK, this should just be like a validity proof, because in this specific case, we're not hiding anything. Insertion and deletion validity proofs. What these mean is that the Merkle tree, essentially whenever there's a new user, so let's say that you download the World app, you just get verified at the orb like right now, you need to get inserted into this set of verified users, right? So the way that we do this is that instead of inserting one user per transaction, we batch them off-chain, and then we create a zero-knowledge proof, or in this case, it's just a validity proof. We're not hiding anything. So we just create a validity proof, or a SNARK or STARK, right? So let me just make that explicit here, SNARK or STARK, that we're inserting new public keys into the tree, so new nodes into the tree, and this will create a new state of the tree, like new root hash in the end. So we're using zero-knowledge proofs, or validity proofs in this case, for creating proofs of insertion and deletion. So if you, let's say, want to delete your world ID, you can also request deletion. Or if you, let's say, want to rotate your public key and get a new one, you can also do that using world ID reset. So this is like why we also use SNARKs or STARKs in Semaphore, like in our deployment of Semaphore. Traditional Semaphore doesn't have this, but World ID, since we have so many transactions, like we have 6.6 million users, I believe, right now, or over that. So there's a lot of users that are getting signed up. So if you do one transaction, one user, it's too much, it's too expensive. So we batch them in batches of 1,200 users at a time, currently, also using validity proofs for that. Right. And so this Merkle tree, as I'm showing here, it's deployed on Ethereum. I can also share you links to the documentation if you actually want to look at the actual smart contract after I finish. I just want to make sure that we get to the end before time runs out. So this Merkle tree lives on Ethereum, and the root of the tree is the only state, only public state that you need in order to verify a zero-knowledge inclusion proof. So if I have a Semaphore smart contract or a World ID smart contract, as long as I have a Semaphore contract that works the same, but I have the latest root of the tree, I can always create inclusion proofs against the latest state of the tree, right? So if, let's say, Brian just gets a World ID and he is just now inserted into the tree, he's not able to create an inclusion proof until I update the state of the tree with a leaf which contains his public key, which now he'll be able to create a Semaphore inclusion proof against the latest state. So as long as I have the latest root of the tree on any network, so it doesn't have to be just Ethereum, I'm able to verify World ID proofs. So for example, the way that World ID is mostly used right now is for claiming grants, like Worldcoin token grants. And this is like where you're using ZK4, right? You're proving that you're a unique user and that you've not claimed this biweekly or now it's a monthly grant. So you're creating a Semaphore proof. And this Semaphore proof is currently verified on Optimism. And soon it will be deployed on WorldChain, which I just see that Agnivo also asked the question before I missed, are you guys working on your own L2? So yes, we are. And the next presentation is going to be about that. It's going to be about WorldChain and the OP stack and what that is. So that is going to be the next topic. I forget which date, but it's going to be soon. I think it's Monday, maybe. I'm not sure, but I have to double check. Cool. Hopefully all of this is clear. Sorry if I'm going a little bit fast, but we're racing against time here. So if you have any questions, feel free to leave it in the chat. I'm always available even after this. So if you have any like specific things you don't understand, or you want to go deeper, or you want to get a specific fact, just let me know, and I can answer that for you a bit later. Right, so we can go back to slideshow mode, so it's more full screen. Cool. So when it comes to identity protocols or projects, WorldCoin is one of them. But when it comes to identity protocols, there's a lot of new innovations that have been happening that are purely enabled by technologies like zero-knowledge cryptography. So I want to introduce some of the concepts here. This is a distillation of one of my articles I wrote. Let me just post the article right here if you want to learn more about that specifically, which goes in depth into like modern digital identity schemes. This is just a small slide that is distilled from that, and it's part of what we do at WorldCoin. So yeah, so to introduce this concept, there is a notion of, in order to make a proof about some identity, right? Like I want to like right now in WorldCoin, in World ID, you're proving that you're a unique human, right? So you're making a proof about yourself in some capacity. But essentially you have some provenance, right? Like how are you proving inclusion? Well, the provenance is that WorldCoin and Tools for Humanity and the Foundation and eventually many other parties are creating or curating this Merkle tree of verified humans by using the orb, right? So this is the origin of provenance, like the origin of truth. The orb, this hardware device, is the thing that provides the truth of what a human is and what a human is not, right? In this case, like if you're not in the World ID tree, then you can not use the fact that you're in the tree, right? Like you just cannot make a proof about that. You're just not in the tree. So if the orb is the arbiter, is like the source of truth in this case of what a human is in the World ID protocol. So this is the data origin or provenance. So there's many different types of data in the world. Like you have a lot of different data, like digital data about you, and it lives in different places, right? You may have interacted with Ethereum. You've done a transaction sometime. You may have swapped a token for another token. You may have done, I don't know, bought an NFT. Like all of that in the end turns into data on the Ethereum database, right? So every single Ethereum node will store that data. And so now you're able to create a Merkle proof that your specific data is included in the Ethereum Merkle tree. And you can prove to anyone that you've done this transaction because you can also sign a message and you can prove that you own an address, for example. So this is like the notion of provenance in this case. There's other data besides on-chain data and World ID, of course, right? There's KYC data, for example. There's things like passports, right? So there's information that is stored in your passport, your identity card. There's things like your web data, right? So maybe you have the Facebook account, maybe you have a Google account, maybe you've interacted with YouTube or with the video game or whatever. There's some data that you've created. Maybe if you're playing a game, the state of the game is some data also, right? Or maybe you have some credentials, right? So maybe you've completed university, right? Like you've graduated from Stanford, from computer science. That is a credential that is issued to you. It can be issued by virtually anyone, right? Like my doctor can issue that I'm sick so that I can go to work. And with that credential, if I send this credential from my doctor, I can stay home and I can get my sick benefits, or I can just have a day off or whatever. There's email data. I receive an email. All of these things are data that has some provenance. And using modern day cryptography, you're able to prove the provenance of that data. So I'm able to prove that this comes from a website, this comes from the chain, like the Ethereum, this comes from a credential that was issued by Stanford, whatever. The way that this is constructed is using digital signatures. And the sort of trust that I'm putting is the trust on the issuer, right? So if let's say that Stanford has their private key compromised, then someone else, an attacker, can create invalid proofs of having completed Stanford. And then somebody else, like a company, can be fooled by this signature because it's a valid signature from the valid registry, but it's somehow slipped through, right? So the root of trust, or the provenance root, is a digital signature, or root of, or like chain of signatures, right? Like a signature can sign a hash of some data, and then like you have some root, right? You can keep verifying these chains of signatures all the way to some issuing authority in the end. This is how a lot of the internet works also, with things like DNS records. Like Uber.com is tied to some IP address, and there's some root authority that has some credentials that are signed, and this is a really important critical infrastructure of the internet. And also there's things like Merkle tree inclusion proofs that we've seen before, right? For example, Semaphore, this is a Merkle tree inclusion proof. It's just private because it uses zero knowledge cryptography. So now that we have this notion of what data is and how you can prove provenance, you can start making statements about it, right? You can start making these so-called attestations or verifiable attestations, because now that we have things like zero knowledge cryptography, or maybe you've heard MPC from a previous talk, or maybe you've heard of trusted execution environments, or TEs from the orb side, for example. There's essentially a lot of different technologies that allow you to make statements about the data. I can do a zero knowledge proof like I did with Semaphore, that I'm part of the tree without revealing who I am. That is an attestation. I have some data, the Semaphore tree, and I'm proving that I'm part of the tree without revealing who I am. That's like programmable cryptography tool that I can do. It's an attestation. I'm a unique human, and I've not done this action before. It's an attestation. And so now that we have lots of different data and lots of different ways of verifying that the data comes from somewhere, we're able to do these more elaborate attestations, right? So I can prove that I'm a unique human, then I can maybe take my passport and I can create a zero knowledge proof of my passport. I can create a proof that I'm over 18 and that maybe I'm a citizen of some country, like in my case is the Czech Republic. And then I'm a unique verified human by World ID. And maybe, I don't know, my score on chess.com, my ELO is over something. I have a profile on Twitter or X that has more than X followers. You can start making these attestations and combining them together. And this is what I believe that like modern digital identity rails will be built upon, because they're just much, much better than current systems. The reason why current systems don't work the way they do is that everyone has siloed data. And not only is it siloed, but it's custodied by the third party. It's not custodied by the user, right? Like my data is owned by Google, Meta, like all these companies, Amazon, whatever, and they own my data for me. And then they're able to reason about the data themselves. So they're able to tell that I'm a unique human because I'm paying for 5 different services, and I've had the account for 9 years and it's been active for 9 years, whatever. So these things are what create your digital identity today, and that's why they're able to reason about it today. And the root of trust is the fact that you've interacted with the system in a way that looks human. But this really breaks down in modern day and age because you have AI, right? AI is able to act like a human, write things that a human would write, do things and interact with applications the way a human would. And so this is like what is breaking the internet right now, and why World ID is important, for one. But it's not just about World ID. It's just in general about creating digital identity tooling that is privacy preserving, it's composable, and it's much, much better and trust minimizing, right? Like I'm just creating mathematical statements about data in a way that anybody can verify, and it's secure and safe because of the mathematical properties of these cryptographical constructions. and I don't have to trust some Google party or some third party that is verifying some data or whatever. And they're also having a really hard time because of AI. So this is like why I believe these things are important, why I think you should believe that these things are important, and why it's even worthwhile learning about these things. So yeah, now that we have this notion of identity, attestations, data, provenance, and all sorts of different things, as I mentioned, they can be composed, like they can be combined. I use this analogy of Legos. And DeFi, maybe you've thought of like money Legos. I can borrow from Aave and provide some like collateral to some other lending protocol, and then I can borrow against that, and I can provide liquidity on Uniswap, and then I can put that into a yield aggregator or whatever. There's these Legos that you can compose because it's Ethereum, right? Like everything is in the same thing, in the same system, and it can interact with one another. So the same thing happens here. I can use my world ID, and then I can use my Ethereum attestation service or my Gitcoin passport. I can combine that with some other product, like whatever. And I can make statements about all sorts of different things. And this is the thing that is cool about this, or what I believe that modern, or if we fast forward 1 or 2 years, what digital identity systems will look like, assuming that we continue at a similar pace that we are right now. Just to mention some names of some teams that are building some of these things. For web proofs, there's teams like the ones I mentioned, same for proof of passport, storage proofs, proofs of email, and various others teams that are building programmable cryptography tooling besides Worldcoin. Yeah, and a lot of them are grantees, for example, from the Worldcoin Foundation. We gave a grant to Rarimo, to Open Passport, to Axiom, Herodotus, ZK is in the works, and we've worked to some extent with some of the others here. Yeah, so this gets me into what are the current challenges that Worldcoin is experiencing, right? Like now that you see what zero-knowledge cryptography is, more or less, now that you see what we do with zero-knowledge cryptography, with Semaphore and some of the other things, like ZKML with Modulus or MPC with Tasio, or a few other things that we've been doing, I want to introduce to you like what are the problems that we work on, or like why is this even a thing? Like we can just be done with it and move on, right? There's something else you can do, we can work on. But yeah, there's a few constraints that Worldcoin has. Also, Brian, I'll get to your questions in a little bit. There's a few problems that Worldcoin has that are unique to the problems that we have, or like these problems are unique to Worldcoin because of the scale and the solutions that we have. So for one, the zero-knowledge proofs that we create are created on users' phones or by users because the users have their private key, right? And since users have the private key, right? The private key meaning the private key that belongs to a public key in the Semaphore tree. And since I mentioned before, the prover needs to have completeness, meaning the prover needs to know the witness. And if the witness has a private key, the prover needs to be the phone of the user, because only the phone of the user has the knowledge of the private key. So the only way that we can create a zero-knowledge proof in this case is if we create a zero-knowledge proof on users' phones. So this has a set of like not so great outcomes, mostly because these zero-knowledge proofs are very intensive. It's a lot more computationally intensive to create a proof than to just do the computation, right? So as I mentioned before, there's this notion of succinctness. So succinctness means that it's a lot easier to verify a proof than to just do the computation, right? So the verifier just verifies the proof and they're done. It's quite cheap and easy. The thing that is hard is creating the proof, right? So creating the proof is the opposite of succinct. It's a lot harder to create a zero-knowledge proof about some statements or some computation than just doing the computation, right? So you're essentially, the property of zero-knowledge proofs is that you're offloading work onto the prover so that the verifier doesn't have to do barely any work. And this is really useful because you can then create these systems in blockchains, for example. Instead of having everyone have to verify the same computation, just one computer in the blockchain does it, and then everybody else just verifies. And this is like the good property in distributed systems, for example, that make zero-knowledge proofs really appealing. Same for us. But this problem is that now you're having to do something that is really expensive on a device that is not performant at all. It's a phone. And since we have like millions and millions of users in different markets around the world, phones are unevenly distributed, right? Like if you go to the Bay Area, everyone has the latest iPhone in San Francisco, in the US. Everyone has the latest iPhone. They have neural engine cores with GPUs and a fast CPU, state-of-the-art CPU, lots of gigs of RAM, 12, 16 gigs of RAM to work with. So it's really performing really fast. But if you go to some other places, then you can maybe have a phone that only has 2 gigs of RAM, right? Or maybe it has only a CPU that only has 2 cores. So you cannot parallelize computation across multiple cores. Or even they're running on old architecture. So some of the libraries break and other things, right? So essentially, this means that there's a lot of client-side proving. Client-side just means that it's happening on the phone as opposed to on a server. You cannot do it on a server because otherwise you'd leak private information from the user, like the private key, which you don't want. If you want privacy, you have to do client-side proving. And so this is like why we're working on things like client-side proving. Then there is another concept, which I mentioned right after, which is delegated proving. Delegated proving is essentially using multi-party computation, which is the thing that Lucas talked about briefly in the MPC talk. You're able to delegate work from the client to a server without losing this privacy. But then there are some other types of overhead, like networking overhead, right? You now have to talk over the network, and this might create some bottlenecks because if the user wants to delegate a proof to a server, they might still have to have a good internet connection. And some people not only don't they have a bad phone, but they also have a bad internet connection. So delegated proving might also not be an option. So there's just a lot of different constraints that directly stem from the fact that we have lots of users that are distributed across the world, and some of them have different devices that they're working with. And so if you want to be inclusive and support as many users as possible, you have to directly work on these things to make them better. And it's not even about this, right? Let's say that Semaphore is fairly cheap to do. It's a really small zero-knowledge proof. The size of the thing that you're making proofs of is fairly small. This is called the zero-knowledge circuit. The circuit of Semaphore is quite small. But if you want to do things like proof of passport or proof of whatever, like a storage proof or anything else, like web proofs, these other circuits, other applications that use zero-knowledge cryptography are much, much bigger. So it will take a lot longer, and it's much more computationally intensive to do those. So even if you have a good phone, some things on good phones are unfeasible. So let alone on bad phones. So this is like one of the things that we're working on. Another thing is that we're creating millions and millions of proofs, and these proofs have to be verified somewhere. And in our case, we're verifying them on Optimism and soon WorldChain. And so these proofs create so much demand, but that at one point we were about like 60% of Optimism mainnet. So 60% of a blockchain means that you're consuming 60% of the traffic or of the capacity of the network. So even if you had more proofs, if you had more users, the network would be literally unable to process those transactions because it's full. Like it's not able to process more, not able to verify more proofs. So we're working with other teams like Nibra, Axiom, and Satori through Worldcoin Foundation grants to do proof aggregation. So essentially, instead of verifying one proof, you verify like 10 in 1 or 100 in 1 or 200 in 1. And so that reduces the on-chain footprint by a lot, very substantially. Or you can do the opposite. Instead of submitting less proofs to the chain, you can just make the chain bigger, right? So you can verify more proofs. And this is like the thing that I'm going to be talking about next with WorldChain and the OP stack. And yeah, there's other things I mentioned, right? Like zkML with modulus, also really computationally intensive, a really hard computation to do. And so, as Daniel and Ryan mentioned, we have less than 1 gigabyte to work with for the target benchmark. And so it's a hard problem. And yeah, like all of these things that we're building, whether it's the MPC stuff, the ZK stuff, all of these things are creating new problems that are pushing the boundaries of what is possible today with the technology that is out there, right? With the existing phones that are out there, with the existing zero-knowledge proving libraries and toolkits, with the existing hardware, with everything that we have, some of the things that we're trying to do are not possible. They're literally not possible. So they create challenges, and you need to solve these challenges. So this is briefly I wanted to touch upon. I will go through my last slide and try and answer all your questions if I can. So yeah, just to summarize everything, most of these things I've already discussed in previous slides, but I just want to reiterate some of the current R&D directions that we're thinking about currently, so that people that are maybe watching later or maybe in the future, if maybe you guys are watching it right now on live, but if somebody else wants to watch the video later, just so that they can have some easy way to just coming back to this, so they can think of what we're doing at this time, so they can maybe talk to us about maybe working on some of these things. So current R&D directions, we are working, as I mentioned, on better client-side proving, so that you're able to do bigger proofs on the same device, or at least make proofs that were infeasible in some really bad device, bad phone, old phone, make them feasible, right? So there's two main research directions. These are like technical namings, but essentially there's a proving system called Spartan, which was quite promising. Right now we're benchmarking how promising that might be, and there's potentially better options than this. But so this is like one side direction within client-side proving, and the other one is base fault by plus Fry. So for those of you who are not versed in ZK literature, which I assume is most of you or everyone, these are just names of different ZK constructions, so you can ignore it, but it's like things that we're working on. Another one is research on delegated proving. So as I mentioned, you can do ZK proving instead of on the client, on the server, but using MPC, so you don't lose privacy. However, you have some like networking overhead and some communication overhead and some other problems that you need to solve. So we're working on that with Firma. There's also work on proof aggregation, so that we reduce the on-chain footprint of all the zero-knowledge proofs we create using Nibra, Axiom, and Story. All three of them are grantees from the Worldcoin Foundation. So they've already delivered, like Nibra and Axiom have delivered their grants. Story is still working on it. There's like a bunch of different things that will come out of it. Hopefully, some of them will get to production in the coming months. And yeah, I mentioned also all the identity stuff that exists outside of World ID, outside of proof of personhood, right? Like there's proof of passport. We gave a grant to Open Passport to work on this. There's ZK email, which is done by the ZK email team or proof.email team. Web proofs, storage proofs, ZK VMs. There's essentially a lot of these different identity exploration routes that we're just exploring ourselves to see what makes sense, what is feasible today technologically, what can you turn into a product. Because like once something is feasible to be done for lots of people, you can make a product out of it, right? You can do something useful and actually distribute it and make something that impacts the lives of people out there. Then we're working on the ZKML stuff with Modulus and the MPC stuff with Tassio and Verstex. So for the last two, you can watch the previous talk from them. And for the ones I mentioned above, I've talked to them to some extent in the previous slides as well. So hopefully that is enough context. All right, so that should be most of what I wanted to cover today. I will answer questions from Brian because there are several of them. And
there's also some questions in the question tab on the bottom right.
Okay, yeah. I see. Cool, so I'll answer first in the chat and then I'll go to the questions tab really quickly. So what cryptographic methods do Semaphore and Worldcoin employ? How do they compare? So Semaphore, let me stop streaming this. Let me go over here. So I'll just type them out in the chat really quickly. So Semaphore uses a toolkit called Circom to write circuits or circuits. The type of cryptography that is using underneath, it's a proving system called Groth16. And so if you want to look at how that actually all works, there is a good video on YouTube that I created with a podcast team called The Byte Code. So I'll send you the episode to that. I just do a technical walkthrough of all of the technology that we have and actual code. So if you're curious more about the details of how Semaphore is implemented and things that we do, you can watch this video I just shared. You can just search DCbuilder Worldcoin, the byte code on YouTube for those who are listening. Yeah, so it uses Groth16 and Circom for Semaphore. And for the Merkle tree batch inserts and deletions, we use Gnark, a different toolkit, but also Groth16, so it's the same thing. How could Semaphore be used to enable anonymous transactions in the Worldcoin ecosystem? It will not. It just won't. Semaphore is not designed to do that. There's been existing systems who do that, most notably this Tornado Cash. However, that one was labeled by OFAC as something not to interact with. So it's a very complex legal topic. You can search about it. It's quite interesting to learn about. There's other systems that are trying to build ZK privacy for transactions. You can use things like Penumbra or PAYY. There's a bunch of other tools. There's Railgun. Essentially, there's a bunch of other tools. ZK privacy for transactions is not a problem we're trying to solve. There is a lot of other teams that are specifically dedicated to solving these problems. What real-world applications could benefit from the integration of Semaphore and Worldcoin technologies? How does Semaphore and Worldcoin address user privacy and data security independently? Use cases, you can watch the previous video about World ID use cases with Ian. How do Semaphore and Worldcoin address user privacy and data security independently? For the cryptography part, you see how we address it here, like with the Semaphore ZK proof. You're not revealing who you are in the tree. That is one part. If you want to see the biometric side, watch the biometrics talk. If you want to see how the orb works, watch the orb talk. So yeah, those address privacy in their own specific connotations. And if you connect them together, you achieve essentially the state of the art of privacy when it comes to digital identity using World ID. It's the most secure. I'm very confident about this. It's the most secure, more scalable, most privacy preserving digital identity protocol that I've seen out there by far. It's really ambitious, and I'm really proud of what we've built. 9, what potential vulnerabilities could arise from combining Semaphore and Worldcoin systems? So Semaphore and Worldcoin, World ID is using Semaphore, so it's one and the same in this case. So I'll just break it down to that. Problems with Semaphore, I guess the only problem with Semaphore is that it's using a hash function called Poseidon. If you're like doing the security analysis, if anyone is able to break elliptic curve cryptography, which people are speculating because you have quantum computers, whatnot, this might be a potential vulnerability, but it's inconclusive if this is realistically feasible because of how hard it is to make quantum computers. But other than that, there's no other real vulnerabilities, unless there's a bug in the implementation of it, right? Like that's like a logic bug more than a cryptography or system design bug. Then there's potentially, if someone leaks their private key, then you can see the nullifier hashes that private keys ever created. So you can de-anonymize someone if you extract their private key somehow. So that is more of like a device security. If someone steals your phone and extracts the private key, they're able to de-anonymize some World ID actions that are on chain. So that's another one. But it's not really a vulnerability. It's just if someone misuses the system or if someone does something wrong. I want to know about this too, please. What are the key advantages and potential drawbacks of using zero knowledge proofs for digital identity verification as opposed to traditional? So drawbacks is that it's less performant, right? It's computationally intensive. And the benefits is privacy preserving, right? Self-sovereign. You own your own data. You're private. You have your privacy. It's inclusive, so anybody can use it. It's not gated. It's mostly benefits. It's just, I would say it's all benefits to use ZK in modern digital identity systems. The problem why everybody doesn't use it today is because first of all economic models for how these startups are sustained. Like, why do you think Google makes any money? Why do you think Meta makes any money? Why do you think Amazon makes any money? Because they have your data. It's literally that. 60% of Google revenue is ad placement. So if they know data about you, they can do better ads. Therefore, they make more money. That's the reason why they're not using ZK. Can I get your email? I don't really use email that much besides for work. So if you want to DM me, just send me a tag message. I just sent you my link. Cool. Yeah, that's like the drawbacks. Let me go to the questions tab very quickly. How is it possible to use ZK to prove someone is not within a sanction list or a politically sensitive person for the purpose of KYC and AML? Great question. This is actually something that exists. There is a fork of Semaphore, a fork of, for example, Tornado Cash, which allows you to do this. I forget the name of it, but let me actually search for it really quickly. Privacy pools. So for example, privacy pools, let me write it out. Privacy pools. So this protocol is a fork of Tornado Cash, which at the end of Tornado Cash, when you're withdrawing a note or claiming a note, part of the withdrawing a note proof is the fact that you have to prove that you're not in the OFAC sanctioned list and that whatever, like you're not a person that is sanctioned by the US, so you can still interact with the protocol, whatever. So this is like a version of this protocol that might, for example, make it more compliant. In practice, currently it's not, but these are sort of things that you can use ZK for. You're proving exclusion. Instead of proving inclusion, you're proving exclusion. So you're proving that you're not part of the set of sanctioned people or politically sensitive or whatever. It's virtually as simple as doing inclusion. You're just proving you're not in the set you just negate inclusion. So it's fairly straightforward. How does Worldcoin implement proof of membership? How is Semaphore used in this context? I think I addressed that one quite extensively. If you want to see more details about Semaphore, you can go to this link, semaphore.psc.dev. Let me just check. Yeah, it still works. Great, they're still using that domain. Otherwise, I think I explained it fairly at length during this talk. How many iris codes is a person supposed to generate using the orb? So only 2, one per iris, right? Or one per eye, if you will. And what is the timeline for this process? So you go to the orb, the orb verifies that you're a unique person, then it takes a high resolution image of both irises. It's able to compute the iris code within the orb, and then deletes the original images, and it just sends the iris codes to this MPC setup. And with that, you're able to do uniqueness checks against all the other iris codes in a completely private fashion, privacy preserving, because the MPC setup doesn't reveal the actual iris codes. It just does these linear secret share scheme checks. You should watch the MPC talk for that. How many iris codes a person? That's the same question. I asked this in relation to understanding proof of concept. Okay, that addresses it, I think. What is the purpose of orb rescanning? How does zero-knowledge proof enable users through self-custody update the biometry data without needing to return the orb? Users can update their iris data locally. So that is something that is mostly in the works for the second thing that you've updated, that you mentioned. Orb rescanning is a thing that if, let's say, you lose your phone, you lose access to your World ID, you can still go to the orb again. The orb will create an iris code which will match an iris code that is already in the database. So what you can do is you can just delete the public key that is associated with that linear secret shared iris code and insert a new one for that iris code. So that's how you're able to do reset. You're able to reset completely from losing your World ID. But it's a feature that is in the works. It's not yet. But yeah, this is something that you could do as part of World ID 2.0 roadmap for that. Yeah, and the self-custody part. So once you have ZKML, you would be able to do self-custody, because you could, instead of the orb having to do this iris code generation in the orb, you can just store the image of your biometrics on your phone, encrypt it, and then just locally create a zero-knowledge proof of the creation of the iris code, and permissionlessly insert yourself into the MPC set of verified users after undergoing the uniqueness check. So that is something that we're also working on. It's mostly dependent on ZKML becoming feasible and some improvements on the MPC stuff. It's a current R&D direction as well. Cool. I think that does it, unless there's another, last question, informal question. Everyone asks for phone numbers these days, whatever. How do I find a ZK proof for it without revealing phone number, without using eCash, whatever? Pay with phone number. 222. Yeah, that's a simple thing to do. The way that people do it right nowadays, for example, for Signal, you no longer need your phone number. You can just have a username. So you can just share a random username. It can be whatever. And people can discover your contact. This is fairly good for that. For payments, the way that current payment systems work, you really need the card number or whatever. When it comes to these ZK solutions like Pay or whatever, as long as you have a public address, you can send money to that public address without anyone seeing it, or you don't know where it came from. You don't know who you're sending it to. But yeah, you can use ZK for that. Like all these solutions I mentioned about Pay, Penumbra, Railgun have some way of obfuscating payments. However, in the real world, you really do need some form of compliance. If there is a business sending $100 million to another business, it's not something that regulators will like if it's private and they don't have any visibility for it because of accounting, because of taxes, because of other things. So these systems might still need to be engineered so that you're still complying with the legal system. Even you still have privacy. The ideal is you have privacy for every virtual use you want, but you can at least still be compliant. And ZK enables both things. You can selectively disclose things to prove. For example, I can say, the money I'm sending has been taxed. And if you create a proof of that, then you can send it to whomever in a private way and nobody cares, right? Or maybe you have to also send it to someone who is not sanctioned, right? So that you also prove that you're not sending it to someone who you can send it to legally. yeah, these are like all sorts of things that are up to debate for people to explain and to build on. But like in the next 1, 2, 3 years, you'll see this. Awesome, cool. So I think that's it, and I'll get ready for the next presentation on OP Stack and World Chain, coming I think next week.
Great. Sounds good. Thank you for this amazing presentation. Thank you everyone for being so active in the chat. And see you next week.
See you there. Take care, guys.
Bye-bye.
Bye-bye.